Hi everyone, my name is Kevin Sahlin. Today I'm talking about the PC RAM technology, which is phase change random access memory, giving an introduction and kind of a future work type briefing. So PC RAM is a new storage class memory. This is starting to take the marketplace with flash and taking parts of the RAM and disk market as well. It was first discovered in 1968 by Stanford R. Shinsky. These first materials weren't really useful for anything, but eventually in about the late 90s it started being used for DVDs and then Blu-ray discs as well. This used optical phase change memory, which has an optical shift in reflectance as you shift the phase, whereas we're looking at the conductance shift for this memory. These use germanium, tellurium, and antimonide materials for the most part, usually 2 or 3 of them in an alloy, to make the phase change material. One such device is shown here. It's the mushroom cell device, in which you have your phase change material here that shifts between high resistance amorphous phases and low resistance crystalline phases in order to get your shift in resistance that gives you your storage of your bit. So you shift between these states by applying pulses of current. So here you see the reset current pulse, which is very large in magnitude, and it increases the temperature of the phase change material above the melting point. So you create this amorphous section right above the heater. It's then quenched so it doesn't have time to crystallize, and you end up with this high resistance section that gives you a high resistance between the bottom and top electrode. The other current pulse switches you from your amorphous to crystalline phases, which is this set pulse here. This set pulse is lower in magnitude, so you only increase your temperature above the crystalline temperature, and then it's a longer pulse, so it holds that temperature high enough so that you get an entire crystalline phase in between the top and bottom electrode. This gives you a much lower resistance and is what actually gives the memory storage. The read current pulse is much lower, so it results in much lower temperature and doesn't affect the phase of the material. So here we see some of the performance metrics of PC memory. So obviously the main fallback of PC RAM is the 16F² cell size. Not really as competitive with NAND flash and DRAM, but you have very good read time, very short write erase time, the standard 10-year retention, high cyclability in 10 to the 9 cycles, which is much better than NAND flash can achieve, and also operates at a much lower write voltage. And as we'll see later, there's a very strong multi-bit operation possibility with phase change memory. So now going into the switching mechanisms. As mentioned, we're transitioning from low resistance to high resistance states in the material. This depends on the material itself, but usually it's around a 10 to the 5th magnitude shift is possible, whereas realistic cells are more about 10 to the 2nd power, so 2 magnitude shift. This varies between materials, as does the melting and crystallization temperatures and the crystallization times. The current flow through this amorphous region is through Poole-Frankel carrier transport for the lower section of this curve, so you need a very large voltage to get a very small current shift. This continues until we hit the threshold voltage, in which we get a negative resistance and then a much more reasonable resistance, much closer to the crystalline phase. This threshold switching is not really fully understood. It's partially thermal and partially electrical, but it's very important because it allows us to switch between the amorphous and crystalline phases without originally going to the very high threshold voltage way out here that would be required to get a reasonable current that would increase the temperature enough to shift the phases. So instead of just being able to switch from crystalline to amorphous, we can now switch crystalline to amorphous and then back to crystalline phases without having to go to very high temperatures and remaining within memory device specifications. Other than this electrical importance, there's also a lot of thermal resistance importance. So because we're changing the temperature of the phase change material, the thermal properties are of both the bulk and the heater, which is titanium nitride here, the bulk and the phase change material, and the interface thermal resistance are all important because we're trying to get this drive current, the reset current, as low as we can get it so that we can minimize the cell selector size. This cell selector is really the limit of the scalability, what's limiting the scalability right now. So we're trying to minimize the thermal conductivity and minimize the current requirements in order to get these smaller cell structures. So in order to do that, we're looking at smaller contact areas and localizing the current in the thermal environment to just where we want it to go into the phase change material. A lot of the work right now, though, is in the smaller contact area and getting better contacts. So some of the device designs that are used right now for that are mushroom devices, which we talked about earlier, where you use lithography to get this trench with the phase change material on top of it. So you have a small contact, and we usually get around 500 microamps of current with this device. The next device is the edge contact, which uses a horizontal heater element that's very thin through deposition, and you just contact just at the edge of the phase change material. This gives you around 200 microamps of current requirement, so it's much lower than the mushroom cell, but still limited by lithography, as is the trench devices, which are around 400 microamps of current, but try and use a more concentrated effect in the thermal resistance requirement. Going out of the lithography dependent processes, we see the phase change material spacers over here. This is a pretty cool device. It uses some of the self-line double patterning techniques that we've seen through some of the other memory devices that we've seen in the past in the class, to put the phase change material as the spacer on the side. This gives a very thin spacer and a very small contact with the heaters on the edges of the cells. So this actually gives us a very small current drive of about 80 microamps. Now, going into this reset current has to actually be driven through a cell selector. So this cell selector requires a high on current of about 20 megaamps per centimeter squared, and a high on-off current ratio of 10 to the 4th or 10 to the 6th ratio. So you can see a lot of these are diodes and a few more novel devices down here, but they all flirt with the on-off ratio and the on current that was cited here. So in the past, these have been MOSFETs, BJTs, and diodes. MOSFETs are usually around 15 to 20 f squared in cell size. BJTs are closer to 5 to 10 f squared, and then diodes are really pushing the limit down to the 4 f squared cell selector size. So clearly, I mean, diodes would be the most ideal because you get much higher density devices because your selector is the same size as your device. But they're much harder to design and build, so they're much more expensive, whereas MOSFETs, the technology's there and it's very well understood. So now, going away from just minimizing the reset current and the thermal contact, one of the main ways that we're going to increase the storage capacity is through multi-level storage. So this utilizes the 2 to 3 magnitude difference in resistance to store multiple bits per cell. This is done through the device structure or through creating intermediate states. The device structure, you end up shifting your device structure to have multiple phase change layers here. So here you have 3 phase change layers. So you get different states as they're shifting from amorphous to crystalline each. So in the bottom here, your lowest resistance, you're going to have all of them in crystalline phase because that's what's going to give you your lowest resistance. As you step up, one of the cells is going to end up having high enough temperature that it's going to go into an amorphous phase, and then you get a higher resistance. So as you step up to the next state, the next phase change layer will also have an amorphous section, and the final state, all 3 of the layers are going to be in the amorphous state. So this is one way you get a 2-bit operation with the 4 cell states there. We've also seen a 4-bit cell which uses 16 states. This requires the read then write operation that we've seen in other memory device designs to actually program the devices through current pulses, as opposed very, very short current pulses that break up the reset and set current pulses that we saw earlier. So this really is very careful to not overshoot and overprogram the device so that we get very distinct states, as you can see here, the 16 distinct states. So the final way that we can really increase the storage capacity is through 3D integration. The ultimate 3D integration would have the 4F squared selector and also have low temperature requirements, because in the end this is going to be a back end of line process. So you're going to need low temperature requirements so that we don't disrupt the memory devices in the stacks below it as we build stack on stack on stack. So this is really one of the things that's driving PC RAM as an option, is that we can get down to this 4F squared, the minimum cell size, as long as we work in these diode type cell selectors, and that the 3D integration is possible with multi-level cell integration. So the only real trouble that we're running into right now is in the selectors, which, as I discussed, we're trying to limit through lowering the current drive requirement for the reset current, and working better with our thermal contact and our thermal resistance, so that these selectors can get down to the 4F squared size, and we can really compete with flash in the marketplace.